Has anybody ever seen those Russian dolls? They're made out of wood and they fit inside each other. You know what I'm talking about? They're called nesting dolls, you know. And you've got the little tiny one and the bigger one and the bigger one. Numbers are like that. Okay. Now here's a very unusual concept. Numbers are infinite. Like all of these number sets I'm going to talk about today are infinite, but some of them are bigger than the others. So still infinite, but one of them's the little tiny doll that fits on the inside and one of them's the big doll that's on the outside. So we start with the smallest one, which is the natural numbers. Okay. They are symbolized with a bold N, or you can do an N with like a little cross thingy on it. Either way, it's the same. Okay, so the natural numbers are called the natural numbers because they're the numbers that come naturally when you start counting. They're also known as the counting numbers. We start at 1, 2, 3, 4, etc., forever and ever on with no end. You could count until you died, and then somebody else could count until they died, like pick up where you left off, and each person could pick up where the last person left off and keep counting forever. It would never end. So it's infinite, but it starts at 1. So it's only infinite in one direction. So it has a starting point, and then it goes infinite forever past that. The next set of numbers are the whole numbers, which are symbolized with either a bold W or you can do a W with like a little extra line on it. Now the whole numbers are exactly like the natural numbers, except they start at 0. Okay, so we 0, 1, 2, 3, 4, 5. So if they were dolls and the natural numbers fit inside, they would be a really tight fit, right? Because the whole number only has one number more than the natural numbers do. The next set of numbers are numbers that you will hear an awful lot in this and every other math class you ever take from now on. Integers. Integers are symbolized with a Z. And you can do a bold Z, or you can do kind of like this weird double Z thing. Integers are all of the negative numbers and all of the positive numbers. So it goes on forever and ever in two directions. So natural numbers and whole numbers only go in one direction. Integers go in two directions, positive and negative. This has also been described as the positive and negative whole numbers. But you'll notice we haven't had any fractions and we don't have any decimals. At this point, there's like these three inner rings, there's no fractions, no decimals. We just have solid numbers. The next largest group that you have are the rational numbers. Okay, rational numbers are symbolized either with a bold Q, or you can do the Q with like a line inside of it like that. It's not possible to list a list like this of rational numbers. So it's easier just to describe them. So what rational numbers include are all of the integers, okay, which if it includes the integers, it also includes the whole numbers and the natural numbers, right? Because they're inside, that's the dolls inside. It also includes all of the fractions, both positive and negative, and it includes all decimals, but special decimals. So it's all decimals that end or repeat. Okay, So you have to have 3 qualifications to be a rational number. You have to either be an integer, you have to be a fraction, or you have to be a decimal that ends or repeats. And what I mean by a decimal that ends is like 0.25. It's just 0.25 and it's done, right? Or that repeats, you've got like 0.232323 forever and ever and ever and ever, and it's just going to repeat over and over again. Rational numbers are all nice and neat and fit together really well like this. And this is all part of the real number family. What you have over here is your weird cousin, or your creepy uncle, or you know, like how every family has somebody that just doesn't quite fit in exactly. You love them, they're part of your family, but they don't fit into the nice package of the same as the rest of you. Well, that's what we have over here, and that's the irrational numbers. Okay. And the irrational numbers are, I'm going to just put it on the outside, is signified with a bold I. Okay. And the irrational numbers are all of the non-ending, non-repeating decimals. So these are all of the decimals that don't fit into a pattern. They don't end and they don't repeat. Pi, you know the number pi, you all know it's 3.14, right? But you also know that it goes on forever, and they've never found a pattern, and it never ends, and it just goes on and on and on and on and on. So pi is irrational. Other numbers that are irrational, so I'm just going to do some examples. You get pi. Any square root or any other kind of root that's not perfect. Here we also get perfect square roots, right? So like if I take the square root of 4, 4 is a perfect square, so the square root of 4 is 2. But over here, the square root of 2, if you actually had a computer capable, it could take this out for ever in just digits, forever and ever and ever. It's not going to give you any kind of number that's going to be nice and pretty. It's just going to be a string of decimals. So non-perfect squares are going to be irrational as well. And these are all part of the real number family, which is symbolized by an R like this, or a bold R. These are all real numbers. Okay. Because there's the real number family, and then over here somewhere off to the side where we haven't gotten to yet is complex number family, which we won't deal with a lot in this course. That's more of an Algebra 2 concept. We'll talk about it a little bit, but not a lot. Okay, so we're going to identify some numbers. Okay? We're going to start with -4. And I'm going to jump back and forth here. Just, you guys can look on your next over, but I have to jump back and forth. No negatives, no negatives. Aha, negatives. So the smallest it can be is an integer. So you can just write a Z. You know, you can bold it, or you can do the double line Z. Okay. If it's an integer, it's also rational and real, right? Because integers are also rational and they're also real because they fit inside. If I come over here to 3/4, 3/4 is a fraction. None of these have any fractions in it. The smallest it can be is here in this circle, so it's going to be rational. And if it's rational, it's also real. Now on the test, I'm not going to have you list all of them. I'm going to ask you what is the smallest group it can possibly fit into. So you would just list an integer for here. You would just list a rational for there. But for now, I want to go through all of them so that it's clear. Okay. We get a problem like this, where you have a square root. First we need to see, can we take the square root of this number? Yeah, it's a perfect square, right? It's 4. So first you do the operation, if you can, and then you classify it. Well, 4, right here, it's counting number, right? We count to 4, so it's going to be natural, whole, an integer, rational, and real. And I'm just going to do regular letters for sake of space. Okay, 7 is the same as 4, right? It's just, it's a number we can count to. So it's natural, whole, integer, rational, and real. Again, though, on the test, you'd say natural, because that's the smallest it fits into.
So just leave everything out in the test, or?
Yeah, on the test, when I worded it, I would say, you know, identify the smallest number group or something like that. And then the smallest, of course, is the ones on the inside, and then they get bigger as they go out. So natural numbers is the smallest, and you know, the smallest one it can fit.
Oh, it's pertain to.
Yeah. Okay, so square root of 2. Not perfect square, right? I can't take the square root of it. So it's going to be some big, long decimal forever. So it is irrational. And it's also real. I forgot I can bold easier. See, I'm bolding. Okay. Pi 3.1415952 blah 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 forever and ever and ever. It's infinite. So it's a non-repeating, non-ending decimal. That makes it irrational. But it's still real. We have 24 divided by 6. 4.
4.
Okay. We've already done 4, right? So we know it's natural, whole, integer, rational, and real. Now, I didn't put any dots at the end of this. If there were dots at the end of this, if I wrote 3.75 dot dot dot, I'm implying that it just goes on forever. And I'm not implying a pattern. If I wanted to imply a pattern, I'd write 3.7575 dot dot dot. Right? But there's nothing, it just ends. That makes it rational because it's an ending decimal. So, divisibility. Okay, divisibility is the ability to divide evenly. Right, so divisibility, Dividability, basically, is how that word came about. Dividability, divisibility. Okay, so there are some divisibility rules. And you can use these rules basically for things like, if we're talking about fractions and you need to give me the fraction in the simplest form, and the simplest form is reduced. So you have to determine what to divide the numerator and the denominator by. Sometimes that's really easy. If you have 2 over 4, it's, oh, they both divide by 2. Sometimes that's not as easy. So the divisibility rules tell you ways to quickly look at a number and tell what it'll divide by. Okay, so if you divide by 2, that means you're even, which means you end in 0, 2, 4, 6, or 8. Okay, so if you're an even number, all even numbers will divide by 2, period. That one, pretty straightforward. Okay. To tell if a number divides by 3, okay, you want to add all the digits. Okay, so you take that number and you add up all the digits, and then if the sum divides by 3, okay, so I take a big long number, or a large number, let's say okay, I want to know if this number will divide by 3. Okay, I take 2 plus 3 plus 7 plus 6. And I'm going to get 18. 18 divides by 3, right? So that means this number will divide by 3. And if I actually do that division, I'm going to get 792. It will divide evenly because the digits added up to a number that'll divide evenly. Okay, for 4, if the last 2 digits divide by 4, then the whole number divides by 4. So if I have some ridiculously long number, okay, 329,724. I look at these 2 digits right here. This will divide evenly by 4, right? So that means that 329,724 will also divide by 4. And I'm cheating. But here, like, to look at this and it's 24, I know that divides by 4, so I know to bother to divide the whole thing. If this was 25 or 23, then it's not going to work, so I don't try. Like, it's much quicker to just look at the last 2 digits and say, oh, yes, or oh, no, that won't work, than to actually do the division. So these are time savers, hopefully. 5 is another one that's really easy. Okay, if it ends in 0 or 5, it will divide by 5, period. If it ends in anything else, it won't. 6, Okay. If you take the rules for 3 and you add up the digits and it'll divide by 3 and it's also even, so it'll divide by 2, then it'll divide by 6. So use both rules. Does that make sense? Okay. Okay, 7 has a rule, but it's very complicated, so it's easier actually to just try to divide by 7. The rules are meant to save time, not make things harder, so there's no real point. It's kind of the same with 8. I'm going to write down 8, but with 8 it's the last 3 digits. But sometimes that's easier because you can just divide the last 3 digits by 8 and see if it works if you have a really long number. But then sometimes it doesn't really make much difference because if you have a 4-digit number, you might as well go ahead and try to divide the extra digit. Does that make sense? Okay, but if the last 3 digits divide by 8, then the whole number will divide by 8. And like I said, 8 is iffy. Sometimes it'll save you time, sometimes it won't really. 9 is like 3. So for example, if I do 3,645, I do 3 plus 6 plus 4 plus 5, that gives me 18. 18 divides by 9, so this whole number will divide by 9, and I'm going to get 405. It's okay. I'll do it in blue. The rule for 10. If it ends in 0. So to write a non-repeating decimal as a fraction, there are 3 steps. Okay, step 1, we're going to count the digits. Okay. Step 2 is we're going to say and this will make sense when I actually show you how it works. So this number zeros, and then step 3 is to simplify the fraction. Okay. Now, I'm going to rewrite these because I think it'll be clearer if we're going across this way than down. 0.75. I have 1, 2 decimal places. So I'm going to take 75 and I'm going to put it over a 1 with 2 zeros. 2 decimal places, 2 zeros. Familiar?
Yeah, it's just like pre-algebra.
Yeah, okay. 75 and 100. We can divide it by 25. Or 5, if you didn't see the 25, they both end in 5 and 0, so that gives me 3/4. Okay, 0.368, I've got 3 digits, so I'm going to have 3 zeros. Okay. I'm going to be honest with you, when I'm reducing fractions, I usually just go small. 368 does not add up to anything that divides by 3, but these are both even. So I'm going to divide by 2. Which is going to give me 184 over 500, which are, again, even, which is going to give me 92 over 250, even, which is going to give me 46 over 125. 4 and 6 add up to 10. 125 adds up to 8. So these won't divide by 3. It's not divisible by 4. Let's see, 46 divided by 2 is 23, which is prime. So, and this is not even, so there's nothing else that these two will divide by evenly. So, not 6, it would be 8, right? Because it would be 2 times 2 times 2. So if we had gone in one step, we would have come from here. I'll do it in blue. If we had gone from here straight to here, we would have divided by 8. But I don't have 368 divides by 8 memorized, so I could do it in steps. We get to the same place. Maybe you would notice that you could divide by 4, and then you could see that you divide by another 2. Or, you know, maybe you know to divide by 8. It's as long as you get here, it's all the same. I'm going to put 0.5 up here because it's really small. 0.5, I have 1 digit, so I have 1 0, so that's 5/10. Those will both divide by 5. So I get 1/2. Simplify, reduce, same. And then 0.3225. 4 digits, so I have 4 zeros. What would you like to divide by? 5, yeah, okay. So if I divide this by 5, I'm going to cheat. I'm going to get 645. And if I divide by 10,000 by 5, I get 2,000. Am I done? Okay, so I get 129 over 400. If I add these up, I get, what, 12, right?
Yeah.
And that's 4. These don't divide by 3. Not even, so it doesn't divide by 2. Doesn't divide by 5, doesn't divide by 10. You can check for 7, but I'm pretty sure doesn't work. I know it doesn't divide by 11 because 121 is 11 times 11, right? So we're done. Okay. Any questions on that?